Good morning everybody. I am Ravi Kumar Reddy from Civil Engineering Department of this college. I deal the subject Engineering Mechanics for the first year BTech. Now I will just start with a topic called plane trusses. We will see what is a plane truss and what are its uses, what is its objective, and how we solve the truss. Okay. So, to start with, I will just brief about the plane truss. What is a plane truss? First, let us see what is meant by a truss. Truss means a system of bars which are connected at their ends by smooth pins, in the sense which has no friction. Okay. Just if I take 3 bars, I connect them at their ends by 3 pins, as you see in the diagram drawn. These pins are frictionless pins. So, that is to say the definition truss. So, truss is a system of bars which are connected at their ends to form a rigid framework is called truss. Now, why I am calling it as a plane truss? Why? Because you have 2 types of trusses. One is a space truss, another one is a plane truss, what we are going to deal. Space truss, meaning that I think you might have seen the tripod stand which has 3 members from a top joint which are spread around. So, this is the best example for a space truss. So, this we are not going to deal anyway. According to your syllabus, we have to deal the plane truss. Now, let us see what is a plane truss. I already told you that the truss means the system of bars which are connected at their ends to form a rigid framework. The plane truss means plane. A plane will be formed by 2 axes. So, if I take x, y axis, the plane I call it as xy plane. So, the xy plane, if all my bars, all my members will be in this plane itself, then I call it as a plane truss. So, that is what is clearly what is a plane truss. Okay. Just for the introduction, what we do with these trusses, that is the basic thing. Before we start the analysis, we just see what is the use of the plane truss. We generally in our buildings will have beams, columns, slabs, foundations or footings, you call, all these are the building elements. Why you want to go for trusses? Is it okay? So, why you want to go for trusses? Let us say, so this is my one of the cross sections of the building. I have 3 columns, I have a slab over it or a beam over it. Okay. So, these are the 3 columns over which there is a beam. If I do not want this column to be placed here, I want to have a free space here, I want to use this space here completely. I do not want to obstruct this space by a column, I want to remove that column. So, if you remove this column, what happens? You have to go for a big size beam, that is a problem. So, your cost will increase, your risk coefficient increase, you go for a risky one. Why? Because this may fail suddenly. So, that is what. So, if you remove a column, if you want to have a free space, you need to go for big size concrete beam that costs much. So if you want to go for a column free space anywhere, we go for the option is best option is a truss. Okay, that is why you can even practically observe that wherever you have auditoriums, industrial buildings, there you do not want a column in between. We need to have a plain space which has no obstruction. So that we go for trusses. So as the live example you can see in our ground, there is recently built structure which is of laid by a truss over that free space. Just for the performance of any cultural activities, whatever you have, the truss what we have in our campus, as you can very well see that truss as like this. This is the shape what we have the our college campus. Okay, so this is supported by generally a column. We support it by two columns. We have, so these are the supports. This is another support. So as it is, if you cannot if you take the truss to solution, you can't solve. Why? Because this is a 3-dimensional one as a column, and so you need to go for generalization. So you generalize this one to your paper so that you can solve it. So a column support is replaced by a hinge support. This one is replaced by a roller support. I think everybody knows that what is a hinge support, what is a roller support from the initial classes. So I need not go for these two to explain again. Okay. So this is the plane truss I have. Why? Because all my members are lying in a plane, vertical plane, and supported by two supports. Why we want to support this by only hinge and roller, I will explain you in the course of the discussion. Now, so the idea behind why we go for the truss is to have a column free space, and there is another aspect which we have. The truss will have only compression and tension in the members. Say if I take the truss members, I join 3 members, I get a truss, so that I provide with 2 support conditions which are generalized. Okay. So this is a truss. These member, say member 1, member 2, member 3, these members will have only either compression or tension. So this is the best option, another choice of going for why we go for trusses. One is to have column free space, another to have simple loading cases. Simple truss members will be generated by only compression and tension, there won't be any bending at all. Okay. So why? Because the members are strong enough to take compression and tension. That is why we have these two in the truss members. Okay. So this is all about why we go for truss and why we deal with the trusses only. Okay. The option for the truss why we go for is if you have a column free space, if you want to have the column free space, and if you want to have only compression and tension to be taken by your members, that is the case where you go for. Okay. So now next we see the analysis part, how we design these members. I said if you have the truss in our campus, okay, how you hinge and roller, yes. Say hinge support, I said hinge support. Say I drawn the generalized format of hinge like this. If you connect a member to this hinge, what this support will provide is just like this. Say member, I am connecting with the hinge. Okay. So this is my support. So if I rotate this member, I can rotate this member, that is called a hinge. If I want to pull it up, I can't. Okay, if I apply a horizontal force, I can't. If I apply a vertical force, I can't. So there will be a reaction from the support. So if I apply rotation, it will freely rotate. So there won't be any reaction. So hinge will have two reactions. This is all known for all. Okay. So next is a roller one. This is a roller support, which is a generalized one from the practical things. If I connect a member, as I said, there is a roller support will look like this. So I keep the member on this one. So if I apply a horizontal force, this will roll. So this cannot resist the horizontal force, but it can resist vertical force, but it can even rotate. So the only one and only reaction is the reaction. For present setup, it is vertical. Why? Because a roller can be like this. A roller can be like this. So in all these cases, the reactions will be developed perpendicular to the contact surface. Okay. So if this is a vertical roller, the reaction will be horizontal. This is a horizontal roller, the reaction will be vertical. So all these are the support conditions. Why we provide one roller, one hinge? Why not the two hinges? Why not the two rollers? We will just see in the course of discussion. As I said, every theory, if it comes to a formula, you need some assumptions. Okay. So those assumptions what we make to solve the trusses and to make the problem simple to solve. Okay. So the assumptions what we have. So first assumption, as I already told you, with the definition itself, the members of the truss must be connected by frictionless hinges only. Frictionless. So these are all the frictionless. Why? Because if you have the friction here, if you take the friction into account, you need to go for additional force here. Additional unknown will become. So the additional unknown, if you want to solve, you need additional equation. So to avoid that, I assume this as a frictionless support. So that will be the first assumption, frictionless hinges. The second assumption, all my bars should lie in the vertical plane only, meaning that all the, say if this is a member, this is another member, there will be another member here. So the axis of this one, axis of this one, axis of third member, all the axes must lie in a single vertical plane. That is, this is called the second assumption. What happens if these will not be in a line? Say this is the member, if this axis is not in the plane, what happens is your load will be somewhere here, your force will be somewhere here, your member will be somewhere here. Okay, your load will be somewhere here, your member is at a distance. So it will create moment. So we do not want actually the moment, that is why we have gone for the option truss. The truss should take only compression and tension, it should not involve moment. So that is why we do not want to take this as, so that is why this assumption is given. So all the axes of the members should lie in a vertical plane, that is the second assumption. The third one, all the forces coming on to this truss must be on the hinges only, on the joints only. I call this as a joint or a hinge or a pin, whatever it is. So all the forces what I apply must be on the hinges only. So whatever force you apply, that force must be on the hinge only, you should not apply on the member. What happens if I apply on the member? Say if this is some member, if I apply the force on the member, what happens? It bends. So I should not have any bending stresses again. If it bends, it is going to develop some stresses internally. So no bending stresses. I need to have only axial stresses. Because of axial loads, there will be normal stresses developed because of the axial forces. So that is why this is the third assumption. So the load should be applied only on the hinges, and that load should also be in the plane of the truss. The load I apply should also be in the plane of the truss. It should not be like other plane. Okay, it can be like this, it can be applied like this, it can be applied like this, it can be applied like this, but it should not be applied like this, other plane. So it should be in the single vertical plane. Okay. All your support members, load, everything should be in a single vertical plane. Okay. So those are the three basic assumptions we make to make our truss simpler to solve. Okay. So those are the assumptions we have. Next condition. Before going for solution of the truss, first let us see what is a solution of truss. Solution means what you do. So solution means I find the forces developed in each member, how they develop, because I said the truss will be used to create a column free space which will be used by the people for performance of any activity. So let us say this is the truss what I have. So the space, let us say this is the column here, I generalized to a support, there is a column here, I generalized here. So this space I want to use for my performance. Okay, you will have a 3-dimensional figure, but I am going for only a cross section. So this space I want to use. Just by skeletal truss you can't use it, you need to have a roofing material. If you have a roof, you can use this space. So to protect from all environmental activities like sun effect, wind effect, everything, rain effect. Okay. So all these effects must be protected by providing a roof covering material. The roof covering material can be a GI sheet, can be an iron sheet, whatever it is, whatever you place, that will be roofing material. From roofing material we will get the loads at the top. The weight of the roofing material itself is the force coming onto the truss. So my case, my assumption is to have loads only on joints, I should not have loads on the member. That is why what I make is I calculate this total load, I make it into to this joint and to this joint to be applied. Okay. So I apply this total load to this joint, to this joint. So my loads will be only on joints now. So this is how the loading comes on to the truss. Okay. So because of roofing material what we have, or if you have access to the roof, the live load what you have. Okay. Load which the people movement will create the load. If a person walks like this, it creates live load. So those loads, everything will be transferred onto the joints. So solution means I said because of externally applied loads, what are the forces developed? Why? Because this truss is an intermediate structure. This is the top structure which we want to place. As we cannot place the roof without any support, it cannot stand in the air, that is why we need a truss. So truss cannot be in the air, you need to support it. I am supporting by 2 columns. So this load which has come from the roofing material will be transferred to the truss first. All these forces will be transferred like this and finally to the support. All these forces finally will be transferred to the column. So from the column we have the basement, we have the footing will take care of everything to transfer onto the ground. So this is the complete transfer of force from top to bottom. So what we are in is truss. So if this is okay from all the problems, then your roofing material is okay and you can use this space very well. So that is the final objective of this one. So now come to the analysis. So I said because of forces, the forces will be developed in the member. Why? Because say if I take a member, if I apply a force here, if I rigidly support here, if I apply a force here, the member is not moving. Why it is not moving? I am providing a support here. So that is why if I apply say some 100 kg here, this is offering some 100 kg, that is why this is not moving. So this 100 developed is called support reaction. So the 100 is passing through this one, correct. So the force developed in this one is also 100. So that is how the force is developed in the member. What we see is whatever is applied we can see, but the reaction and the force passing everything we can't see. That is where you imagine, okay. So you need to imagine that there is a force, the force is applied, the reaction is developed, the member force induced, okay. So that is how the forces will be developed. Why we need the forces in the members? What for we find the forces in the members? So if I am the designer, if I asked to design the truss whatever is available in our campus, what I do? I go for the analysis, I find the forces in the members, okay. Then what I do is I have, say if this member is made of say some steel material, it is a steel rod, say a steel rod of some 10 mm diameter steel rod I have. So if this member is a member of one of the members of truss, okay. So because of these loads, this member will get a force induced, say some 100 newtons is the force induced in the member force developed in the member. So how can I decide that this member is safe, okay. If this member is safe, if this member is safe, if this member is safe, if all the members are safe, my truss is safe, my roofing material is safe, I will be safe finally, okay. So how to decide this one? The final aim, what we learn now is only to find this, how much is induced in the member because of this loading, that is only we learn here. What is the afterwards work? What we do is a designer will do, or the higher classes what we deal is this one, a design part. This is only the analysis part, okay. So if there is a 100 Newton force, I said the truss member can be a tensile or can be a compression. This will be compression, this will be tension, okay. So what I apply is a compression. So let us say this is the compression applied or developed in the member 100 newtons. Say if I can handle 250 Newton per mm square, this is the value for steel member, steel material. Steel material can take this much of stress. Stress means load by force by area. Force by area we call it as Newton area mm square. So Newton per mm square. So this is the say value for steel. A steel material can take only 250 Newton per mm square stress. So how much is developed here? Okay, you see 100 newtons is the load which is inside the member. The area of this one, this is a 10 mm diameter, so I go for pi d square by 4. This is the stress developed in the member. If this stress is less than this value, your member is safe. If this is more than this one, your member is not withstanding for the developed force. So you increase the size. So if you increase the size, you go for 12 mm, 14 mm, you increase the size so that stress will go down, it will fall below 250, so that you are safe. So that is the afterwards work. So what we deal is only the analysis. So now I come to the actual point, what is to be done in the analysis. So our work is to find how much is the force developed in the member, each member of a truss. So before going for that, we have some special conditions to learn in the truss. Determinacy. Why? Because if you want to start analysis of the truss, you have to know that prior to analysis whether you can start the analysis or not. There is a condition called determinacy. Can you determine or not? Okay, that you have to decide first. So there are two things here. One is external, second is internal. You have to see the truss externally whether you can determine or not. You have to see the truss whether internally it is okay or not. So you have, so I just take the truss, now this is the truss, I supported this truss by a hinge and roller. Externally means this is the truss, these are the things which are external. The truss is kept on this support and on this support, these are external supports. The truss is internal, internal means the members, joints, all are internal, these are external. So the external, whether the externally is it okay or not, can you determine or not. So I said you have two reactions developed for a hinge, two actions if you make there will be two reactions. So two actions, two reactions, 1, 2. For a roller there is only one reaction. Why? Because it can roll, it can rotate. So the only one obstruction is this one. So total 3 reactions are developed from the supports external. Why? Because I have the load here, this load will be transferred all these members and finally it goes to the support. So this load, say if I have 100 kg here, this has to pass through like this, it has to pass through like this, come to support. How much is taken by these two reactions out of this? How much is taken by this one? So that is all lying in external determination. So externally you are having 3 reactions from the basic equilibrium conditions, meaning that equilibrium means stable. So if this is a member, if I have 100 Newton to this side, if I want to keep this member in equilibrium stable, I must apply 100 to this side. This is called equilibrium. So this member is under equilibrium upon these two forces. So there are 3 conditions like this. If you want to say that a member is completely under equilibrium, you need 3 conditions. One is horizontally it should be in equilibrium, vertically it should be in equilibrium, and upon rotation 3. So 3 actions, you have 3 conditions. We provide 3 actions which are most general in the daily life, what we have the structures. So first one is sum of forces in x direction must be 0, sum of forces in y direction must be 0, sum of moments must be 0. So if you can see this equation here itself, 100 minus 100 0, 100 to this side, 100 to that side, 100 minus 100 0. Similarly if you have any vertical force, that must be 0. If you have a rotation, and it must be 0. So all under all these, though there are forces acting, but still the member is stable. So that is what the condition I want for this truss. Why? Because my truss, I do not want my truss to move, I do not want my truss to go down, I do not want my truss to rotate. So it has to be stable. So how I can achieve that stability? If you check for these 3 conditions, then it will be stable. So this is checking. Already I know that because of these supports and force, this is under stable condition. I know that this is stable. So that I use those 3 equations, I find these 3 unknowns. So there is a relation. If you have 3 equations, if you have 3 unknowns, you can solve them, so that you can find what is this reaction, what is this reaction, what is this reaction. So you can find the 3. So this is called external determinacy or indeterminacy. So if you have number of reactions minus 3 equal to 0, then your truss is externally determinate, okay, externally determinate. Till I did not go to the internal condition. Okay. So if the reactions are more than 3, if the reactions are equal to 3, your truss is externally determinate. If your reactions are more than 3, it is called redundant. Redundant means extra supports you are having, extra reactions more than 3. If the reactions are more than 3, 3 means equilibrium conditions are 3 only, your reactions are more than 3, that is why you can't determine, that is why it is indeterminate, or in the other name is redundant structure. So this is redundant. If the reactions are less than 3 and only 2 reactions, let us say 2 reactions, how can we have 2 reactions? By just providing 2 rollers. If I provide 2 rollers, now the reactions are only 2, my unknowns are 2, I do not know this force, I do not know this force, but I know this one, I am applied, this force is applied by me, okay. So these are the 2 reactions, I have 2 reactions only, but I have 3 equations to solve. So this truss can be solved, but let us check the stability of this one. What happens if I apply a horizontal force? This truss will not be in this position, this will roll, will move to some other place. I just can't take my things every time to go to under the truss. So that is the case. So that is why this is not a stable one, it is unstable, okay. So this is unstable case. So prior to start the analysis, prior to start finding what is the force developed in these members, you have to check whether your external supports are according to these conditions or not. If you have this condition equilibrium, then you can start solving only external, till I did not go to internal, okay. Now we will see how the internal condition will be. So after checking the external indeterminacy by using just the simple equation r equal to 3, r less than 3, r greater than 3, all those conditions, now go to the internal indeterminacy. Internal indeterminacy. Internal indeterminacy depends on the, as I said, the internal means it consists of members and joints, okay. So internally whether the truss is determinate or indeterminate. If I connect 3 members, 3 rods by taking 3 pins, just a pin, you connect, you take 2 rods, you connect it by a pin, and you take another rod, you connect it by pins, so that becomes a truss. So simple, the simplest form, basic form for a truss is this much, okay. So this is the one. We have checked the external condition and we have determined finally that we need to have a hinge and a roller, okay. Now the internal condition, say if this is the truss, there is an equation available, m is equal to 2j minus 3, to check the internal indeterminacy. Internally m, oh sure, okay. Last 10 minutes we will provide for that. Oh, okay, okay. So in my lecture, you just as my lecture proceeds, you just can note it down in your just a paper, what and all are doubts in between you have, then you can ask me at the end. I will be providing with 10 minutes of time, so that we clear our doubts here if you have any, okay. Well, let us come to the internal indeterminacy. So members, m means number of members in a truss. In a complete truss, how many number of members are there? Let us take this one, 1, 2, 3, I have 3 members, m is 3. How many joints you have? J means joints, number of joints, 1, 2, 3, I have 3 joints. Okay. So, M means 3 is equal to 2 times of joints are 3 minus 3. It is satisfied, 3 is equal to 3. So, internally the truss is stable. Okay. Now, let us see the other cases also. If I join 4 members like this is also a truss. Why? Because we are connecting the members at their ends by hinges, that is why we call it as a truss. All the members will be in a plane, that is why we call it as a plane truss. So, this plane truss is having, now I check for the condition again. I have 1, 2, 3, 4 members, my joints are 1, 2, 3, 4 joints, joints are 4, members are 4. Now we check this condition. So, members 4 is equal to 2 times of joints 4 minus 3. So, this is 4, 4 to 8 minus 3 5. So, 4 is not equal to 5. So, there is a problem. So, what is that problem? If I apply a horizontal force here, what happens to the truss? It will just collapse, it cannot stand here. So, the shape is not stable. So, this will, if I apply a horizontal force, this will try to deform like this, finally it will deform like this, it will fall down. So, this is the process of falling down. Okay. So, this condition is not satisfied, we know that this is not internally stable. Okay. So, if I want to make this stable, what I need to do is, if I increase this to 5, I can make this stable. So, meaning that you increase one member, I connect a member like this, now the truss is stable. So, from this I can say that the basic stable truss is a triangle. If you have a triangle shape in any type of truss you see, anywhere you see, if you find all are triangles, then your truss internally it is stable. You need not check for this condition, just it is, if it is all of triangles, then you can say that it is of stable truss. Okay. So, members are less, members are less. If the members are less, the truss is unstable or collapsible, it can collapse if the members are less. Let us see if the members are more, what happens. Say if this is the case. Okay. So, if I join another member here, which I do not want actually, for my stability this is well safe, even though if this member is not there, well safe, but still I add a member, what happens? So, I have added one more member here, becomes 6 equal to 5. So, 6 more members are more. So, you can't determine that additional one. So, that is called, it is redundant member, whatever you have extra, that is called redundant member. So, this is called internally indeterminate. If you have this condition is not checked, and if you have members more than 2j minus 3, it is internally indeterminate. If m members are less 2j minus 3, your structure is collapsible, so unstable, collapsible, it will collapse. So, that is the case, 3 cases, m equal to 2j minus 3. So, internally if you want to check whether you can start analysis or not. So, prior to go for analysis, we start doing these things, whether your structure is externally determinate or not, your structure is internally determinate or not. Once we finish off all those things, then we can start up the analysis. Okay. So, these are all the background things what you need to know prior to solve a truss. Okay. So, I think I can stop my lecture at this point. I open the session for discussion.
You tell that the staff members and the operators in the classrooms, they should be open the IP telephone to interact.
Okay.
You can't do 100.
Okay. So, I request all the staff members in the classrooms and the operators in the classrooms to make ready the IP phones, ask them to dial 1000 for any questions they want to raise. Okay. So, I am available here to answer any questions. Okay. Please raise your questions if you have any questions regarding this topic. Not only the lecture what I gave now, even whatever some of the people already finished the topic trusses, and some of them are going to have their classes on trusses. So, you need to clear your doubts, all your doubts. If you have any doubt, you can ask me. I am ready to. You can even give your feedback on the quality of lecture also. Okay. Okay.
Question అడిగింది చెప్పు.
Okay.
The question asked అన్న.
Mute lo pettesi. Now there is a question from one of the rooms. The question is, I said m is greater than 2j minus 3. If m is greater than 2j minus 3, I said there is a problem. Means it is not a problem. this was the truss I drawn to you, and this truss is satisfying this condition, that is members are more than 2j minus 3, members are more than the required number. So somebody asked that what is the problem if you have a truss like this, what is the problem? There is no problem, you can have it, it is over rigid. Rigid, collapsible, rigid, over rigid. This is over rigid, means according to its stability there is no problem, but according to the analysis there is a problem. If you have one more member additional here, generally I did not go to the method actually, now I go to the method. There is a method called method of joints to solve this one. This is the method what we use to solve for member forces in a truss. Okay. So this method basically takes a joint and it analyzes that joint. Say method of joints, if I take this joint, there is a member here, there will be a force in this member, there is a member here, there will be a force in this member, there is a member here, there will be a force in this member. I want to find all these three, then only I can design these members. So because of these three, as you can see, all the forces are concurrent, all the forces are concurrent forces. For a concurrent force system we can apply only two equations, that is sigma f x 0, sum of forces in x direction must be 0, sum of forces in y direction must be 0, then only you can solve this one. So these are the equilibrium conditions for concurrent force system. So this is a concurrent force system, I can use these two equations, but I can't determine these three forces with the two equations. I need additional information to solve these three forces, that actually we do not deal in the first year, but in the higher classes we deal this one. If these will be, this joint will be provided with a known data, that is deformations. We take the help of deformations. There are so many methods to deal this condition. At this level, actually for the first year level we do not go to the indeterminate trusses. Okay, these will be determined in the higher level for the civil engineering people, I say. So this is the problem. According to its stability there is no problem at all, it is over rigid, rigid than what we require, but there is a problem with the analysis. You stop your solution will be stopped at the midway. Okay. So that is why in the first year level we do not solve this one, but in the higher levels we solve. Again I am telling that how can you solve, you have only two equations, you can't solve the three unknowns in this level, but you can solve by with the help of, you need one additional equation, then you can solve this one. So these three can be solved by using the additional information. Okay. So that is what the answer for your doubt. Okay. I repeat the question, there is a question from somebody that we have dealt only a hinge and a roller and two rollers, I said. What happens if somebody asks that, what happens if you have two hinges? Say this is my truss, if I provide a hinge here, what happens is I have two reactions developed for a hinge, I have another two reactions developed for the two reactions. So for the two hinges we have 1, 2, 3, 4 unknowns externally. The discussion what we had just now was because of internal indeterminacy. Now it is because of external. Why? Because you consider this entire thing as a body. Now this is the external thing. So you have externally 4 unknowns, but for the equilibrium of a body under all these forces you have only 3 equilibrium conditions: sigma fx, sigma fy, sigma m0. I think I have explained that one. For a member to be in, for a member or a body to be in complete equilibrium, you need 3 things to be satisfied. So these 3 things are to be satisfied, but you have 4 unknowns, you have 3 equations. That is why you cannot solve this truss. It is internally indeterminate. Okay. Okay. Now, so somebody asked me that the basic question itself. You have 4 unknowns, I just shown you 4 unknowns. So if you have 4 unknowns, why can't you use 4 equations? Okay, we have 3 basic equations regarding equilibrium. If you want to keep a body in a complete equilibrium, I am saying complete equilibrium, this equilibrium concept is developed prior to BC, in the BC somewhere around 720 BC by the Archimedes. Okay. So this concept, equilibrium concept, will deal with the 3 basic actions: horizontal action, vertical action, rotation action. These 3 are the actions which will trouble the member in its equilibrium. Say if I want to keep this member complete equilibrium, in complete equilibrium, I apply an action, say some action which is not in horizontal, which is not in vertical action, but I can resolve this action into 2 actions. So whatever the action on the body, it will be resolved into vertical and horizontal. If you nullify this vertical action, horizontal action, then your member is stable equilibrium in horizontal and vertical directions. Okay. Then there is another criteria, that is rotation. If you nullify this rotation, then your member is in complete equilibrium. So for complete equilibrium you have 3 actions. If there is action, there will be a reaction. So 3 reactions will be developed. So if the 3 directions, sigma fx0, fy0, m0, you can develop these 3 equations from the basic equilibrium concept. You can use only 3 equations, not more than that, for any type of system of forces only in plane. I am talking about only in plane. If you go to the space structures, you can use more number of equations. That is not actually in your syllabus. Okay. Your syllabus is restricted to only the planar forces. In the initial classes itself, your engineering mechanics is divided into 2 categories. One is of plane forces, space forces. So that is the conclusion, okay, from this. Okay. Still any more questions? If you have, you can raise to me. we have a question, why can't you provide one hinge and two rollers? Now the question is, why can't you provide one hinge and two rollers? Let us see what happens. Say let us say this is a truss. Somebody asked me that why can't you provide a hinge and two rollers? Where you provide? Why? Because I want a column free space. I need not have, I don't want to have any support in between. I don't want to have any support in between. So you need to support only at the ends, only at the ends, or there is another type of structure which can be given as something like this. So this is a truss which is supported only at the one end, and you have a cantilever portion so that you can have this space as a free space to use. So this is a truss. You said one hinge, two rollers, why can't you provide? I need only two supports, you choose one of them, okay. So my compulsory condition is one hinge, one roller. Where you provide the other roller? If you provide in midway the support roller, another roller here, your space is restricted to only this one. So your space restriction is gone. So that is why you need to have only two supports to have simply supported condition. I think the classes what already been dealt by plane trusses, so they might have got this classification: simply supported, cantilever, and the some other truss type called inbuilt one. If you have a truss like this, this is called inbuilt. Why? Because there won't be any support, external support here. We take the member into the foundation itself. That is called inbuilt support. So these are the three support conditions. So I should not have like this. That is why I need to go for only two. Why? Because my column free space, if you have a column here, what is roller means? You need to have a column here. So it is obstructing. My basic requirement is I don't want to obstruct my space, okay. So that is why we don't go for three supports. Still any more questions? You can raise your questions. Okay, thank you for listening to me. I think we had a great time. Meet you in the next lecture. Thank you. Okay.
Hello, is a small announcement. I request the operators and the staff members who are handling these demo lectures, DMS lectures in various classrooms. You close down. The lecture is over for today. The two DMS lectures are already completed, and any more questions and other things you can be dealt in a regular class work, or otherwise in any other DMS class which is going to take place in the coming future. All the operators and teachers, you close down the things, the amplifiers, you keep it in the regular box, the shelves, and lock it, and the key of that amplifier, IP telephony, and also the laptops. So you carry with you and keep in your own departments. Whenever required, we call again. Thank you very much. Thank you indeed.